So in the previous tutorial, we did look at the introductory part of system modeling, and today we want us to look at the transfer function of electrical systems or electrical networks. So when you talk about the transfer function of electrical networks, then basically what you're talking about here is how do you develop transfer function given an electrical network. So in this case, we usually use several laws of electrical, the basic laws of electrical engineering, and in this case, to be specific, we usually use the Ohm's law and the Kirchhoff laws. So what are the various steps of coming up with the transfer function, or deriving the transfer function of electrical system? When you want to derive the transfer function of electrical system, then the first thing that you are supposed to do is that you are supposed to come up with, the first thing is you are supposed to come up with what we call the integral differential equation. Integral differential equation. You're supposed to come up with integral differential equation. Integral differential equation. You develop integral differential equation for that particular network. So after developing the integral differential equation, and this one is always by the use of KVL, that is the Kirchhoff voltage law, and the Kirchhoff's current law, or the KCL. So after doing that, then you can now take the Laplace transform of all this equation and then eliminate and decide variables. So after that, take the Laplace transform, take the Laplace transforms of the equation, then eliminate the undesired variables. Eliminate the undesired variables. Then after you have, of course, the first one, developed an integral differential equation, then you, after taking the Laplace transform, then by transposition and arrangement, obtain the transfer function. Then by transposition and arrangement, obtain the transfer function. Obtain the transfer function. So those are the three easy steps that are going to guide us in order to obtain the transfer function of an electrical system. So we can start by looking at a very, very, very simple example that is going to help us to obtain the transfer function. So we can talk about, we can have an example. So an example under electrical systems, we are going to look at several examples in order to try. So we are going to, in order to understand how to obtain transfer functions of electrical networks. So we are just going to look at this simple one. This is going to be a first order. So obtain the transfer function of the electrical network shown below. So in this case, we have this network. So the first thing that we can look at is we can get to the Kirchhoff. We can define it, whereby we can say, what is EI? EI is equals to the voltage that goes through R, or we can simply say the voltage that goes through R, where we can talk of VR, plus the voltage that goes through the capacitor, which we can say as VC. And from here, we can see that the voltage that goes through the capacitor, or we can use E, because it uses E for consistency, we can use E. So we have ER and EC, that is, and if you look at the voltage that goes through the capacitor, we'll see that EC is also the same as E out. And therefore, we can simply say that EI is equals to ER plus E out. So that is what we have. So after that, we can now express the voltage in terms of E out, in terms of the capacitor. So we can now express the voltage in terms of the capacitor, and then just by reminding ourselves, we know that Q is equals to CV. Then we know that IT, which is Q, the quantity of charge, is also equals to CV, and therefore we can simply say that V in this case, no, we want to express I because I is common to all of them. We want to express I, so we can make the I to be the subject of the formula, and if we make I to be the subject of the formula, we can simply say that I is equals to C V over T, of which we know the only thing that is constant here is the capacitance, and therefore we can say that I is equals to C dV all over dt. And what is our V in this case? E out. So we can simply say, with the reference to what we have there, then we can simply say I is equals to C dE out all over dt. And from here, we can make the equation where we have the I. So if we express this, we are going to say EI is equals to IR. The current that passes through there is IR plus E out. It's IR plus E out. And what is I? Our I is C dE naught dt, which means EI is going to be now, so wherever we have I, we replace it with that equation where we are going to have RC dE naught all over dt plus E naught. And with that, now we have dealt with the first part of how to obtain the transfer function of electrical network. That is, you are supposed to obtain what we call the integral differential equation, and this is now what we refer to as the integral differential equation. And of course, just to remind ourselves, this is still in T domain. That is still in T domain. So that is what we refer to as the integral differential equation. Then after obtaining the integral differential equation, we can now obtain what we call the transfer function by taking the Laplace transform and then transposition in order to obtain the transfer function, and we shall have obtained the transfer function of that particular network. So in that case, we now say the second part, taking Laplace transforms. When you take the Laplace transform, when you take Laplace transform, when you change them to the time domain, we always write them in capital letters. So we can say E I of S is equals to R C, and then d dt becomes S E of S. It should be E out of S plus E out of S. And then we can now say EI of S is equals to E out of S, then we put it into bracket, RCS plus 1. Then from there, we make E out over EI of S to be the subject, and therefore we can now say that we make that one to be the subject, and if we make it to be the subject, we can now say that E out of S all over EI of S is equals to 1 all over RCS plus 1, and that is the transfer function of that particular system. That is the transfer function of that particular system. So you can see where we started from, defining all the voltages, then we obtain the integral differential equation, then taking the Laplace transforms, then by transposition, rearrangement, in order to come up with that. We can look at another example. We can also look at another example on electrical systems, and in this case we have that particular circuit whereby we have the inductor and also the resistor at the output. So just the same way we did that, we did the previous examples, we are going to look at how do we obtain, the first thing that we are supposed to look at is how are we going to obtain the integral differential equation. And that one we can get it from, we express that one as EI is equals to, we can talk of EI to be equal to In this case, the voltage as a result of the inductor VL plus the voltage as a result of the voltage drop at the resistor. So in that case, but we also know that the voltage drop VR is also the same as V out. Or to be consistent, we can talk of E. We can talk of E. EL and then ER. Then this one we can talk of ER is the same as E out. And then with that, we can also say that EI is the same as EL plus E out. And what is E out? We want to express this in terms of current. We want to get the current that goes through that common current. Then the common current, we want to express the common current in terms of E out. And we know that from the resistor, V is equals to IR. So I is equals to V all over R. So in this case, what is our V at the output? E out. So in this case, I is equals to E out all over R. And that is what the current is. So when we come back to our equation, EI is going to be, we know the voltage drop at the inductor is always given by L di all over dt and then plus E out. L di over dt then plus E out. So in that case, we can have I. We can replace I with that, and therefore the equation will become EI is now going to be L d all over dt times E out also over R. And therefore, we are going to have L over R d E out all over dt plus E out. And of course, all these are in terms of time domain. Then from there, we have achieved the first step, whereby we are supposed to come up with the integral differential equation. Then now, from after doing this, we are supposed to now get, take the Laplace transforms. Then you can say taking Laplace transforms. If you take the Laplace transforms, we can now say, of course, when taking Laplace transform, we are going to write in capital letters. So we are going to have EI of S, and then change it from time domain to frequency domain by getting the Laplace transform is equals to L all over R d. No, d becomes S. So we have S, d dt becomes S E out of S plus E out of S. Plus E out of S. Then from there, now we've taken the Laplace transform. Now we can rearrange this in order to make E out over EI to be the subject. Then you can say EI of S is equals to L all over R. Now we can put S, we can put E out of S outside. Then that is going to be L all over R S plus 1. And that is now what we have in this case. So that is what we have in that case. Put that one into brackets. Then we can now say E out of S all over E I of S is going to be given by 1 all over L all over RS plus 1, of which if we rearrange, then we are going to have R all over LS plus R. And that is the transfer function. That is the transfer function. And that is now another example on how to obtain the transfer function. This is still a first order system. So maybe we can look at a second order system, and then we can look at further examples in this. So we can still look at further examples. So we can look at another example of a system, and the equation is there. I show that the RLC network shown below is a second order system and derive its transfer function. So the transfer function can be derived. If you get the transfer function, then that one will tell you whether it is a second order or a first order. Of course, a second order will have the second derivative of the differential equation. So when you talk about this, just the same way that we were doing before, then we can have a voltage drop at that point, VR, a voltage drop at that point, VL, and a voltage drop at that point, VC. Then, from now, we can simply say VI can be given by VR plus VL plus VC. So, that is the first equation that we are going to have. Noting that the VC, that is the voltage as a result of the voltage drop as a result of the capacitor is also equals to the V out. And therefore, we can simply say that VI is equals to VR plus VL plus V out. Then we can now have the current here and express the current in terms of the element that is at the output, which is the capacitor. We can do that, and from there, we know that from there we can get Q is equals to CV, IT is equals to CV, then I is equals to CV over T, of which the capacitance is the only thing that is going to be constant. The rest will be changing, and therefore we can say that I will be C dV all over dt. And when we do that, now we can say that our VI now, VI will be equals to, what is here is IR plus, what is here is VL, the voltage drop by the conductor is L, di all over dt, plus V out. So, we can now express all the currents in terms of V out. Of this, in our case, I is now going to be from that definition. If we try to customize it, it will be C dV out all over dt. So in that case, wherever we have I, we are going to change it to C dV out over dt. And therefore, VI is going to be, of course, it's VI of S, is going to be I, and what is our I? C dV out over dt. So we are going to have RC dV out all over dt plus L d dt times I. And what is our I? C dV out over t dt, which is now going to be LC d squared V out, because that d dt will be multiplied by dV out dt, and therefore we are going to have that one, and therefore, of course, that one is still in time domain, not that is still in time domain, and then here plus V out again in time domain. And with that, we shall have obtained what we refer to as integral differential equation. So this is the most important part. After you've obtained the integral differential equation, then from there you can now come to taking the Laplace transforms. And you say taking LTs, taking the Laplace transforms. If you take the Laplace transform, d dt will become S, d squared dt squared, d squared over dt squared will become S squared. And maybe I usually prefer arranging them in terms of the highest order. So don't think whether that one will make any significant change, but it is always good to arrange them in that one, so that we have LC d squared V out over dt squared plus RC, of course, in t domain, plus RC dV out all over dt plus, of course, again in t domain, plus V out again in t domains. Then now we can now take the Laplace transform. Taking LTs, taking the Laplace transform, then we can say VI of S is now going to be LC, then d square, that one become d squared over dt squared will become S squared V out of S plus RC S d dt becomes S V out of S plus V out of S. Then we can now put V out into outside the bracket, then we are going to have Vi of S is going to be V out of S into LCS squared plus RCS plus 1. And then that is now what we have. Rearranging in order to get the Laplace in order to obtain the transfer function, output, the Laplace transform of the output over the Laplace transform of the input. Now we are going to have V out of S all over Vi of S is equals to V out is equals to A1 all over, it's now going to be 1 all over LCS squared plus RCS plus 1. And with that, you shall have answered the question. Show that the RLC network shown below is a second order and derive its transfer function. So this is the transfer function. To show that it is a second order, that one has been shown even from the differential equation, from the integral differential equation that we had here. You can see that it is a second order because d squared over dt squared is a second order. It is, and therefore that one has shown. Even you can still use the s squared here because the power of s also determines the order. So if it is s squared, then that one signifies that it is a second order system. So we can look at, this one looks a little bit complicated. We can look at this example, that's example 4, whereby we are asked to obtain the transfer function for the network that is shown below. And this one, now we can look at it in terms of using the KCL, the Kirchhoff laws. We can always obtain the integral differential equation. Then from the integral differential equation, we can have the transfer function. So from this, the first thing that we are going to do is that we can see that the voltage, this one being parallel, the voltage between the voltage at R and also at that point being parallel, it means that we only have V out is equals to the VL plus VR, or we can talk of VR, and we know that VR in that case is going to be the same as VC, and it is also going to be the same as V out, and therefore we can simply say that, not VI, this one should be VI. VI is going to be given by VL plus V out. So we can simply say that from that particular analysis, because this one being parallel and it also the same as that, so it means that the VC is the same as the VR and it also the same as the V out. And then what is going to be different here is that the current that we have, we know that the current that we are going to have in this case is going to be, I is common to this, and then we know that I is equals to I1 plus I2. And we can now define both I2 and I1. If you look at I1, maybe we can have I1 is going to be given by V out all over R. That is what is going to give us I1. Then after obtaining that, we can talk of I2. I2 now is what is going through the capacitor, the current that is going through the capacitor, and the current that is going through the capacitor will be given as C dV out all over dt. It's going to be given as C dV out over dt. And now, if we write this in terms of differential equation, we are going to find that it is going to be, what is going to be at the inductor, that is L. So, our VI now is going to be L di all over dt, of course, of t, that is also of t, plus V out again also of t. So that is going to be our differential equation. So after obtaining that particular differential equation, after we have obtained that particular differential equation, we know that I is equals to I1 plus I2. So from that, we are going to use this. We are going to expand this and then do the expressions as per what is there. So in that case, we are going to say Vi of t is going to be given as L d dt, and I is I1 plus I2 plus V out also of t. So of course, that is still in terms of t. And therefore, we can now say that Vi of t is equals to L d dt into what is I1? V out all over R plus what is I2? C dV out all over dt. And then close the bracket plus, of course, this is still in time domain, t plus V out. So this is what, if we simplify, then we shall have obtained the differential equation. We shall have obtained the differential equation, and that is now what we are going to have in that case. That is now what we are going to have in that case. So we can say Vi of t is equals to L d dt V out over R. You can have that one, L over R dV out dt. L that R there, V out dt, plus L C, L times C, then d dt will now be d squared V out all over dt squared, and then of course this is still in time domain, that is still in time domain, plus V out of t. Maybe we can rearrange. I like the highest order to be the first one, so we can have Vi of t is equals to L C d squared all over this t squared V out of t plus L all over R d dt V out of t, L over R d dt V out of t plus V out of t, and with that you shall have obtained the integral differential equation. And next time is taking the Laplace transform and then rearranging in order to get an expression for the transfer function. So we come to taking Laplace transforms, rather taking LTs. Therefore, we can now say Vi of s is going to be L C s squared V out of s V out of s plus L all over R, that d dt becomes s V out also of s plus V out of s. Then from there, we can simply say that Vi of s is equals to, we can factor out V out of s, then we talk of LCS squared plus L all over R s plus 1. Then that is what, if we simplify, then we are going to have V out over Vs, V out over Vi, and both in S domain is going to, we are going to have, we can have 1 all over LCS squared plus L all over RS plus 1, of which if you simplify, then we can have that one as so you can simply have simplifying that. Therefore, we are going to have R. If you simplify that, then we are going to have V out all over Vi of S. We are going to have that Vi over Vi of S is going to be given by, of course, R all over LCS squared R plus LS plus R. And that is now the final transfer function. That that is now the final transfer function that we might have. That is now the transfer function that we can have for that case. So we can also try to obtain the transfer function just as in the earlier examples, but this one is a very important circuit. This one is a very important circuit that you will meet most of the time. It is very commonly used in under system performance. It is always used in what we usually refer to as damping, and again it is also used in compensation systems. So it's a very important electrical circuit. So I want us to obtain the transfer function of this. Maybe this one we are going to do it differently from what we have done before, and we are going to obtain the transfer function by giving the expression of both of what we have. So when you talk about this, we can talk of VI of t. The VI of t is the same as the voltage that is here, and we can use the method whereby we find the voltage by the use of the resistance in parallel to get this, to get the impedance there, so that we can simply say that if they're in parallel, then we can simply say that there is a common I for both. So we can simply multiply I, then the total impedance in parallel, which will now be R1 times 1 over j omega c all over R1 plus 1 all over j omega c. So that one will give us the impedance that is here plus V out, which is simply I R2. So this I is common to both. So that one is an expression on how we can get the transfer function. So we know that in transfer function, j omega can always be replaced by s, and that is to say that V1 of t, Vi of t can be given as I into R1, then all over R1 all over SC all over SC all over R1 SC. So that one is going to multiply that. S j omega will be S SC plus 1 R1 SC plus 1 all over SC. So that one can multiply that, then plus I R2. So that is what that is all about. That is what it is all about. Then from there we can simplify what we have here. So if we simplify this, we are going to get Vi of t, of course, that is also of t, Vi of t is going to be R1, we can have it here, R1 all over, it will be R1 SC, because that is going to be, that is going to multiply that. It's going to be R1, R1 SC, of course, R1 all over. So if we divide, we are going to multiply by that, then the 2 will cancel. So we are going to have R1 all over R1 SC plus 1 over R1 SC plus 1. So that is now what we are going to multiply by I, then plus R2, I plus I R2, and of course both of these are in t domain. But we know that the transfer function is given as V out all over Vi. Then if we do that, then we are going to have I R2 all over the whole of that all over R1 all over R1 SC plus 1, then this one, of course, plus R2 plus R2, then the whole of this one we can multiply by I, of which I is common to both, and therefore we can have that one to be simplified. We can simplify that one further. We can simplify that one further so that we can have R2. So we are going to have R2, therefore V out over VI is going to be R2 all over. Of course, that is going to multiply R2 into R1 SC plus 1. That is going to go up there. So this is going to multiply up there. Then all over R1, plus R1 plus, we can talk of R2 into R1 SC plus 1. Then now, that is now what we have. If we simplify that, so with that, you shall have obtained the transfer function. So this one you can still, have it in such a way that you can still expand it, and then that is now what we have as the transfer function. So if we have that, we can now with that you already have the transfer function, but now you are told to express alpha in terms of 1 plus S tau all over 1 plus alpha S tau. So in that case, we can divide all parts of the equation, dividing the equation, dividing the expression by R2. So we can divide the expression by R2. So in this case, we can talk of that one up there. We divide by R1 plus R2 by R1 plus R2 in order to make it to be that way, so that we can now V out over VI is going to be R2 all over R1 plus R2 into R1SC plus 1 all over R1 all over R1 plus R2 plus R2 all over R1 plus R2 over R1 plus R2. Maybe what we can do is maybe we can expand it so that we have R2, so that we have R2 R1 AC all over R1 plus R2 plus R2 also all over R1 plus R2. So that is now what we are going to have. So if we simplify this, then this one will become the alpha. So that is going to be V out all over VI is going to be alpha into R1SC. So we were told that R1C is going to be tau. So this one is going to be S tau plus 1 all over R1, this one plus this one. It is like we are saying R1 plus R2 all over R1 plus R2, and therefore it's 1. So that is going to be 1. Then from here, we have R2 here. This one here is going to give us alpha plus alpha. Then R1C is going to give us tau. Then we have S. And with that, you shall have expressed that transfer function in that manner. Maybe this one, maybe there is no harm in changing that, because there is nothing that you are going to make to change. So you can simply say that it is 1 plus S tau all over 1 plus alpha S tau. And with that, you shall have expressed it. So this one you are going to use it when we'll be talking about system compensation. So that is all as far as the transfer function of the such kind of system is concerned. So that is much as far as the examples are concerned.